All right, we're going to start our next unit on momentum, but before we move on to our unit for momentum, we're going to look back on our previous units, and here's why. You have different physical situations that you're analyzing using your physics tools. And right now we have kinematics, forces, energy, and now we're going to add a new tool, momentum, to the mix. But the only thing is, sometimes people get a little confused once they have all these tools in their toolbox. They don't know when to take out which tool for which job. So I'm just going to do a little recap just to kind of keep in your mind. And you should write this down just because it's kind of like a little guide to kind of keep you focused on what tool goes with what. And I'm not saying you can't solve certain questions using kinematics or energy, but sometimes a problem lends itself to a certain tool just a little more easily. So, unit one, we talked a lot about math. We talked about one-dimensional kinematics and two-dimensional kinematics. So, all kinematics was something flying through the air, position, velocity, acceleration. It described how an object moved. What are you looking for? Like in a question, like what's the big tip off that you're going to use a kinematics tool? So if you need to hit pause and think about this, what are we looking for when you know you're probably going to use kinematics? So we're back. The big tip offs for me, something flying through the air, and maybe they're asking for time because time's in our kinematics equations, well, most of them, and or it could be an acceleration of a race car, something coming to rest or something like that. But the big tip off that's a kinematics question is probably something flying through the air. Okay, or they're asking you if you write down your givens, you get position, velocity, acceleration, or time. Those are pretty good indications if you write down those givens and have a want of one of those variables that it's probably going to be a kinematics question. Then from kinematics, we went over to the forces unit and we have to know Newton's laws. So make sure you go back and review Newton's laws. Law number one, also known as the law of inertia. An object at rest stays at rest. An object in motion stays in motion unless acted on by an outside net force. So really important, inertia is not a force. Inertia is a property of matter, as Bill Nye would say. And so if you have mass, you have a tendency to keep doing what you are doing. If you're at rest, you want to stay at rest. If you're moving, you want to stay moving unless there's an outside force to your system. Okay, that's law number one. Law number two, we used it over and over again. It was force equals mass times acceleration. Remember where you do the squiggly E, the summation of forces, we'd set it equal to m times a. There were two situations when we could set it equal to zero. Either the object wasn't moving, so there's no net acceleration, or the object was moving at constant speed or velocity, so it was just moving the same rate the whole time, so there was no acceleration. And so just keep in mind F equals ma unless the object's not moving or if it's moving at constant speed. And we're looking at unit two. Ask yourself, what are you looking for? Like, so you're on the AP test, what types of questions say I'm probably going to be using forces as a tool? So hit pause if you want to and think about that for a second. The big tip-offs to me that you're probably going to be using forces as a tool, if they ever say draw a free body diagram or label the forces, like on a free response question, you're probably going to be using forces as a tool. Or if you see a ramp, a pulley, any type of cable question, you're probably going to be using forces as a tool. Okay, so kinematics, stuff flying through the air. Forces, they might ask you to make a free body diagram, and that's a big tip-off. And a lot of times in the FRQ, the free response questions, they'll say, hey, label your forces on this dot. Probably a pretty good indication you're going to be using forces. Ramps, pulleys, cables. And one thing to keep in mind, sometimes they can ask you a question, and we always have to remind ourselves of this. Back in kinematics land, position, velocity, they would give you the acceleration. Well, in forces land, we had sometimes set the solve for acceleration, right? Well, remember what the link is between these two tools. If you can ever get the acceleration using your forces, then you can go back and use your kinematics equations. So acceleration's the link back to kinematics land. And remember, in kinematics, it's always important to find time if you can find time. All right, then we're going on to question or unit number 3, which was energy and work. We just finished it. Energy and work. The cool part is these are vectors, right? You need position, velocity, and acceleration. You need magnitude and direction. Forces, you need magnitude and direction. Energy and work, they're scalars, which just mean you need the number, the magnitude, 10 joules, 100 joules. And one thing some people will say, Laurent, but you know, negative joules, that means you're losing energy or it's leaving your system. But it's not like it's not like you're saying 10 joules at an angle of 30 degrees. You're not really assigning a direction to the energy, like, yeah, it floated at 33 degrees and 33 and a half degrees. So energy is a scalar, okay? And what are you looking for? Think about it for a second. The big tip-offs for me on energy, maybe you have a curved roller coaster track and you have potential converting over to kinetic and it's gravity doing work, so it's EF minus EI equals 0, and you're going to use the conservation of energy. And Sometimes even with ramps, we've seen that we can solve ramp questions using energy. So we could do PE converts over to KE. So the one thing that's a little bit tricky about energy, some of the questions you can do with energy, you could also use forces. And just to recap, we had a question like this toward the end of the last unit. You had a car on a ramp or some block on a ramp. You used forces to get the acceleration, and then once you knew the acceleration, you went over to kinematics to find the velocity. So you could use forces and kinematics for a ramp type question. But what we learned in the energy unit, you could just do EF minus EI equals 0 and transform your potential energy over to kinetic. And as long as there's no outside work, you'd set equal to 0. Now, key, if there's ever any outside work on your system besides gravity, which remember gravity is a conservative force, if there's any outside work, then you have to do the whole EF minus EI equals work. And don't forget that work is the force you're talking about. If it's friction, it could be FF times the delta X, like however long that force is acting over, whatever duration delta X it's acting over, times the cosine of the angle between those two vectors right there. And keep in mind for friction, friction might be going to the left, the object's moving to the right, so that'd be 180 degrees. Cosine of 180 is -1, and that makes sense because energy is being removed from the system. So just to recap, kinematics, something flying through the air. Forces, pulleys, ramps, cables, you gotta tilt your coordinate system, all the good stuff you know. Energy and work, sometimes it's a little bit hard to identify. It could be something flying through the air. You could use energy probably, you know, kinetic and potential. It could be a ramp. You could do PE converts over to KE. But the big tip off that it might be, if you had to decide between using energy as a tool or kinematics, if they ever ask for time, we don't have any time things in energy. So that'd be a tip off that it's kinematics, okay? So that's just a recap of where we've been. And if you're a little confused, go back and watch it again or look back at your old problems. But that's where we've been. And here is where we are going. And one thing to note, all of these things so far are linear or translational is another word for moving in lines so far. Momentum, we're going to talk about linear or translational. I call it linear momentum. But unit 5, we're going to start talking about circular motion, so not just moving in straight lines. We're going to move in circles, just like when my dog Penny tries to chase her tail. It's cute, kind of sad, but pretty cute. So unit 4, momentum, and we're back to vectors. So if you want to write this down, unit 1, kinematics was vectors, or it was a vector. Position, velocity, and acceleration were the 3 examples of the vectors we talked about a lot. Force is a vector. Energy and work are both scalars, so joules, 10 joules of energy. Scalar, just need to tell the number. Momentum, that is going to be a vector, so it's going to have a direction. If it's moving left, the velocity will be negative, and we'll talk more about it. Momentum is a vector. Really important, what are we looking for? Collisions. If you ever see objects hitting each other, you're going to use momentum as your tool, okay? Objects hitting each other, a big tip-off, collisions. I always think like if you ever play pool and you have that cue ball and you use it to break and spread the other billiard balls across the table, that's a big collision right there. We are looking for collisions, and that's a tip-off that momentum is going to be the tool. And collisions could be 2 things coming together or 2 things exploding apart, okay? So unit 4 momentum, linear momentum if you want to write it down, because we do have angular momentum to talk about coming up soon. First things first, we have to talk about what is momentum. And we hear things like, oh, that team's won a lot of games in a row, they really have some momentum. Or that team's really lost a lot of games in a row, they really don't have any momentum. That's kind of like those little common sayings. But like we know it has momentum. If you have a semi-truck traveling down the road at 70 miles per hour, you'd say, that semi has a lot of momentum. If you had a bumblebee just sitting on a flower, you'd say that bumblebee doesn't really have much momentum at all, and if it's just sitting there stationary, it has 0 momentum. So you know momentum has to do with certain factors. It has to do with an object's mass. And if you want to picture it, it's kind of like an object has mass, so that has inertia, so it's kind of like inertia in motion. So, or you could say mass in motion. Mass in motion is probably more accurate, okay? What is momentum? It has to do with an object's mass, okay, like the semi-truck example. It has a big mass, but it also has to do with velocity. And you don't want to say it has to do with speed because momentum is a vector and velocity is a vector. So it has to do with mass and velocity. And even before you know any physics regarding momentum at all, you kind of have a gut instinct that if you have more mass, then you have more momentum. I'm going to put I was going to say mom, but I'm just going to write it all the way out. If you have more velocity, like a semi-truck cruising down the road really fast, you have more momentum. We have some things. Momentum is a vector, so you're going to have to include a magnitude, so your answers will have a number, and they'll also have a direction, okay? going back to like the x hat or x hat, y hat, z hat directions or ijk, just make sure you put a direction on there. A lot of people get the number and they're like, oh great, I got it right. And it's all about the process, the number, and you gotta include the direction. So there is a very simple formula for momentum. Momentum equals mass times velocity. So just like we said, if mass gets big, this side of the equation gets big, that means this side of the equation is gonna get big. If the velocity gets big, it's like a teeter-totter. If this side of the equation gets big, this to balance it, this side of the equation gets big. The most momentum you could have a big massive object with a high velocity cruise like a semi-truck, it'd have a lot of momentum. And just a side note, mass is measured in kgs, velocity is measured in meters per second. So when you times those two things, momentum will be a kilogram meter per second, which is the same as a Newton second. Just a side note, if you're not into the labels, you can fast forward, but don't fast forward. Remember, mass, F equals ma. Mass is a kg. Acceleration is a meter per second squared. They call it kilogram meter per second squared. Once you're famous, they said, hey, Newton, let's just call that a Newton so we don't have to write it all the time. A Newton second would just be that ugly mess right there times a second. Second cancels one of those seconds. So a Newton second is the same as that kg over s. If you didn't like that, don't stress about it, but you can always reason out units based on, oh, m times a, well, m's a kg, a is meter per second squared. So you can always reason things out like that. But the big thing you gotta know, momentum equals mass times velocity. Now, one little thing, the symbol we use for mass is lowercase m. The symbol we use for velocity, lowercase v. What's the symbol they use for momentum? They can't use lowercase m, they actually use lowercase p. Momentum, and I know it's weird, it should have a vector symbol over there, and velocity is a vector. Mass isn't a vector, it doesn't have a direction. Unless for me at the holidays, I've been eating lots of carbs, so my direction of mass would be up, but that's not a thing, don't write that down. So let's see here. Newton's cradle, I don't have one at home here, but maybe I'll splice one in the video. A Newton's cradle device, that's like that office device where you pull one ball back and it goes click, clack, click, clack, just like that. I'll pop one in the video here. But the big idea is this. You can find out an object's momentum just knowing its mass and its velocity, okay? And one of the biggest ideas in physics is the conservation of momentum. Anytime you hear the word conservation, that's code for whatever you start with is what you're gonna finish with. Conservation of momentum, the total momentum of a system is the same before and after a collision. You might have an initial momentum, pi, and sometimes, remember, I get a little lazy with my vector symbols. I shouldn't get lazy with them. Whatever the momentum is at the beginning, it has to equal the momentum at the end. And you might be thinking, Laurent, we kind of talked about that with conservation of energy, EI equals EF. It's the exact same thing. Remember, I'm going to do a little side note here. We said, oh, EI, conservation of energy equals EF. Then I subtracted that over and I said 0 joules equals final minus initial energy. If these two things really are equal, if I had $10 in my bank account and you took away $10, there should be zero difference, right? So if I had final energy minus initial and there's no outside work being done, for energy, that meant it was equal to 0 joules, right? So for momentum, we're gonna kind of play the same game. Actually, your brain's gonna catch on this super fast. Pi equals PF, we'll subtract it over. So if that's true, the Pi equals PF, if you ever take the difference between those two things, it should be equal to 0. And actually, I don't care if you call it a kilogram meter per second or a Newton second, it's the same thing. It should be equal to 0 kilogram meters per second. I'm jamming it in there for the label equals. So they actually, as far as I know, they don't have a name for that. They just call it like a Newton second or kilogram meter per second. So maybe someday when you're famous physics students, you can get it named after you and then, give a shout out to your old physics teacher, okay? One little thing, they say, oh, take the difference, PF minus PI equals 0. So delta P would be equal to 0. And remember, just like with energy, EF minus EI equals 0 if there's no outside work. Well, PF minus PI is going to equal 0 as long as there's no outside impulse. So we're going to talk more about that, but we're going to wind this video to a close right now just because that's your intro video to momentum. So jot it down, and yeah, I hope you enjoy. We're going to take it up a step in the next video. Thanks for watching.